So we talked about confidence intervals for proportions. We talked about hypothesis tests for proportions to test a claim. Sometimes there may be problems when we do a confidence interval or a hypothesis or a significance test. So this is the example we're going to look at, that, and then a couple of other examples, a couple of follow-up studies where there were some, it's sometimes you don't, even if you have a really good study or a good experiment, you may get a weird result resulting in an error that you actually, you accept some claim that really you shouldn't have. Because remember, like, for example, hypothesis tests, we accept it as long as it's under 5%, right? Okay, well, what happens if that result was a really weird sample and it just sort of happened by chance? Well, we've made an error. I mean, it was not a deliberate error, but it was just an error in the probability, like just a weird result that happened just remotely. But we'll talk about that in a second. Anyway, we're going to talk about measles and autism. So you can see a timeline here. In the 1910s, the US averaged 6,000 measles deaths per year. In the 60s, that went up to 3 to 4 million. Finally, in the later 60s, a modern measles vaccine was developed. And then since that time, in 2000, the World Health Organization said that measles has now been eliminated from the US. But then in 2019, the US had the largest number of measles cases since 1992. So all of a sudden they spiked. Why did that happen? Well, one of the reasons is this guy, a doctor from the United Kingdom. And what he did is he did an experiment, and I'll talk about why I use the air quotes in a second, saying that autism was linked to the measles vaccine. So a lot of people accepted that, and then they didn't get measles vaccine. And then that caused a spike in measles in different areas of the world, including the US. So the question is, do vaccines actually cause autism, specifically the measles vaccine, or they call it the MMR, the measles, mumps, and rubella vaccine? So here's his study, which actually has now been officially retracted. In other words, because it was seen as a bad study, and we'll see why right here. He observed 12 children that were referred to his lab, and they had autism or some sort of related disorder. All of 12 had received the measles vaccine. So the study suggested the vaccine and autism might be linked. And then, like I said, it got carried away. You know how people can get carried away with conspiracy theories, and they'll believe anything that the internet tells them, okay? So this caused people to be skeptical of the vaccine, not get it for their children, and then all of a sudden there's measles cases. So based on his study, would it be possible to establish a causal link between vaccines and autism? So what we want to do, this was, like I said, an experiment. And remember the 4 components of an experiment back from Unit 4. Comparison group, random assignment to the groups, replication using a big enough sample or using big enough numbers, and controlling for other variables that could cause confounding. So in his study, let's look at the 4 components. So comparison. Did he have 2 groups, one that had autism and one that did not? No. No. Okay. So and didn't compare with non-vaccinated patients. Because who knows, maybe there's plenty of non-vaccinated patients out there that could develop autism because of some other explanation. Random assignment. Did he take his sample and randomly split them up into two groups? No. Okay. Subjects were not randomly assigned to groups. It was just one group, a group that had autism and got the measles vaccine. Replication. Well, subjects. Is that a big number? No. Only 12 subjects. That's so far he's violating everything that represents a good experiment. And finally, control. Well, this kind of relates to the comparison because he didn't use non-vaccinated patients. How do we know that non-vaccinated patients could develop autism for some other reason that wasn't accounted for? Okay, so there were really no controls. He didn't control anything. And so perhaps the patients develop measles, or sorry, develop autism. For some other reason besides the vaccine. For reasons. But he didn't account for any of these. And who knows, maybe it's because babies or children develop autism because they do or do not sleep in a crib, or they do or do not sleep on certain types of flooring, or, I mean, who knows? But there could be some other explanation. There's plenty of other explanations out there. So basically, this is a bad experiment because it violated all the main components of what makes a good experiment. And that's why it was retracted. And so he actually stopped short of saying that vaccines, the measles vaccine causes autism. But of course, you know, it was already out there suggesting that this might be the case. And then, you know, the media can get it, can carry it away. And then it becomes this big story. And all of a sudden people are not getting vaccines. But even today, even though his thing was retracted, he's a vaccine skeptic. There's another guy in the States who's about to become, probably about to become the health secretary in charge of all the health in the States, who's a COVID vaccine skeptic. He thinks that perhaps that causes autism. Robert F. Kennedy. Okay? So there's plenty of people out there pushing bad causation statements based on poor study or experiment. So we have a bad study design, leads to bias or confounding, okay? And therefore, as a result, we get some incorrect conclusion. However, sometimes a good study, most of the time, it will yield a correct conclusion according to how we do statistics. But by chance, maybe you get a really weird sample or a really weird random assignment if you're going to do an experiment. Okay, you just get some wonky number, like you just get two groups. You know, maybe it turns out that you do a good experiment on seeing if measles vaccine causes autism, but somehow in your random assignment to two experimental groups, one group, you know, were all had vaccines and were all had autism. It's very low of that happening, but it can happen. Okay. So like I said, bad study designs creates bias or confounding, which leads to incorrect conclusions. But when a well-designed study or experiment that we do all the, our size that we use, the sample size is big enough, we've accounted for a bunch of other factors that could come into play, we can still get a weird sample. Anyway, get a weird sample or a weird random assignment just by chance, even though it's remote, and it leads to an incorrect conclusion, which can have an impact, which we'll talk about shortly. Okay. So in statistics, we call these type 1 and type 2 errors. And I'll explain those in a second because there's two, well, no, I'll explain it in a second, I'll leave it. Okay, so at the University of Tokyo, there was a different study done related to Wakefield's study. And in this study, they used oxytocin. Tocin? Yeah. Oxytocin. Yeah, tocin didn't sound right. Anyway, it's a bodily hormone that has positive impacts on social behavior. So it promotes relaxation, trust. Scientists hypothesize that treating autism patients with oxytocin could alleviate some of the core symptoms. So they did a matched pairs experiment. So all of a sudden, it's better. Okay, if you remember a matched pairs experiment. They used 17 subjects that received both a placebo and oxytocin. So each 17 was tested within themselves. So they went for a while with oxytocin, and then things were measured in terms of relating to autism. And in this, what was measured was eye contact time, like whether somebody could focus on something. Okay. And then for a while, they received the other treatment, a placebo. And then their eye contact was measured. Okay. And a coin was flipped, or it was randomly chosen, like each of the 17. You take the first person and you say, okay, heads, you're going to get the oxytocin first and then the placebo. Tails, you're going to get the placebo first, then the oxytocin. Okay? Which is signs of a good experiment. So what makes this experiment equipped to better infer causation than that Wakefield study? So again, comparison. We didn't have two groups. We actually had 17 groups because each person was their own group because they received two treatments, right? So it was a matched pairs design. Where each person, subject, was their own group. In other words, they got both treatments, but randomly. The oxytocin and the placebo. So that's better. Random. Well, within each group, which is each individual, it was randomly decided which treatment they received first. That's good. What would you say about the replication? Remember how many there are? Yeah, still pretty low. Eh? So it can potentially still be a flaw. Potentially still a flaw because that's pretty low. So it's not perfect. And control, well, control for the placebo effect, assuming that it was at least single blind, the patients didn't know which one they were getting first. By giving each individual or each subject a placebo, as well as oxytocin. So better, much better. Much better. Perfect, but much better. Okay. So here's how they did it. And this is kind of practice setting up the state part of a hypothesis test. They measured the proportion of patients who had higher eye contact when taking oxytocin compared to a placebo. They used the alpha at 0 or 5% significant level, or 5% alpha level, you can call it, which means that when we did all the calculations, remember we were looking for the p-value, the probability of the alternative happening, and if it was really low, that's unusual. So that means that we would lean towards the alternative hypothesis. If the p-value was really high, that's not unusual, which means we would lean towards the null hypothesis. Nothing changed. Okay. So how do we set this up? So this is kind of practice from yesterday. What would the proportion be? What do you think the proportion would equal? Remember, in the null hypothesis, p is always equal to something. What do you think the proportion would be? Like no change. There's no indication that oxytocin helps autistic people. What do you think it would be? Wouldn't it be like 50-50? Right? Because if there's no difference, right, then that means it's basically down to a coin flip. And a coin flip is always 50-50. Okay? We want to test to see if the majority of patients improved. So the majority, remember, is 50%. So we want this. We want to see if greater than 50% improved. Whereas if there was no change, it would just be 50-50. And remember, where P is the true proportion who had higher eye contact. I'm just rephrasing the question. When taking oxytocin. Okay. So if there was no advantage, it's 50-50. If there is an advantage, it's more than the majority. The majority cutoff, which is always 50%. So you can see here, we would say in a world where oxytocin has no effect, proportion would be 50-50 or 0.5. We would only expect half the subjects to show more eye contact and half would show less. Like I said, like a coin toss. So the graph below shows how many simulations of possible study outcomes among the 17 subjects, assuming that there is no oxytocin has no impact. And you would expect it to group around 50-50. Right? That's what you would expect, like you see here. But when they did, oh, here, I'll write this. So we would only expect half the patients to have more eye contact. Which means less.
So what actually happened when they did it? 76.5% showed more eye contact. That's a pretty big proportion, quite a significant amount over what we would expect to happen if we assumed there was no impact, right? So it's 76.5%. I don't know, we're looking somewhere around here. And it turns out that this section here, 76.5% and greater, only occurred, if we simulated this several times over and over again, only occurred 2.5% of the time. Which is less than our alpha level. Okay, it's very rare to get a result like that, which means it's unusual. And if it's unusual, that suggests convincing evidence for the alternative, that it does in fact have an impact. Okay. So this result is highly unusual. Only happens 2.5% of the time. Is less than our alpha level of 5%. So because it's unusual and because it's less than the alpha level we've set, the significance level we've set, we have convincing evidence that it is effective. So we would, remember how we said it, we would reject the status quo, we would reject the null hypothesis, and we have convincing evidence it is effective. Oxytocin is effective. So very encouraging result. So encouraging that what would happen to follow-up studies. So based on this one, there was another follow-up, where there was a follow-up study done to this one at Duke University in the States, right? Even better, they used 250 subjects to either receive oxytocin or placebo. It doesn't say whether it's a matched pairs or whether they took the 250 and randomly split them into two groups. But they found no significant difference. So they got a result, a probability that wasn't unusual. That's what that means. Right? So given the results of this study, how is it possible that the smaller Tokyo study showed such a significant benefit from oxytocin? Well, maybe the one reason we could explain is because of replication. The number that they used was so low. Or just by chance, they got a really weird result. So something happened, like maybe it was all the 17 that they chose. For some reason, maybe while they were on the placebo, they had increased eye contact. And when they were on the sorry, when they were on the placebo, they didn't have increased eye contact. When they were on the oxytocin, they did. Okay? For some reason.
And that's why we got it, but that wasn't actually the case.
If we would have picked another 17, maybe it would have been, maybe that probability would have been more like 52% or something, much higher. Okay, or maybe that probability would have been 25%.
Who knows? So the Tokyo result, the positive one, was likely an error because of chance. Remember,
We normally set an alpha level of 5%. Okay, what that means is 5% of the time we could be wrong. It's possible to make an error because we didn't say we were looking, we didn't set the level, alpha level, like it's at 1% or 0.01%, something really, really low. Okay, like if we would have set the alpha level at 1%, well, that Tokyo study, remember, it was 2.5%, we wouldn't have convincing evidence if we would have set the alpha level lower.
okay. So when that happens,
There's two types of errors you can make.
so a type 1 error is when you reject the null hypothesis, you reject HO,
But it's actually true. It actually turns out to be true, is say if somebody did follow-up studies. Okay.
and this happens whatever your alpha level is percent of the time.
For some explanation, we get a really weird sample or really weird experiment. And we get a result that if there were follow-ups done, that it wouldn't be right. Okay?
So we call the alpha level the type 1 error rate. Now, what can we do to reduce that?
Decrease the alpha level. Make it smaller. Right? Make it harder to reject HO. Yeah.
What's that? Here, alpha percent of the time. Alpha percent of the time.
Yeah, sorry, I was squeezing it in there. Okay.
You could lower the alpha or significance level.
But what's the problem with that? You could make a type 2 error.
That's what the problem, the trade-off of doing that
is you increase your chances of making what's called a type 2 error,
which is the reverse of a type 1.
Remember, type 1 means you reject HO when you shouldn't have. Type 2 means you don't reject HO when you should have.
So I'm just saying it sort of like in the reverse. So when you fail to reject, okay, what turns out to be a false null hypothesis. You should have rejected it, but you didn't. Okay? So type 1, yeah, I know it's probably a little hard to wrap your head around at first, is when you reject HO, okay, but you should have accepted it. You shouldn't have rejected it. Okay? Type 2 is when you don't reject HO, but you should have. You should have gone to the alternative. And this chart kind of explains it, right? So if you reject HO, but it turns out that HO is actually true, that was the type 1 error. If you don't reject HO or fail to reject HO, when you should have accepted the alternative hypothesis, that's a type 2 error. All other situations is correct. Like if you reject an HO and it turns out that the alternative is true, good. If you don't reject HO, but then it turns out HO is true, good. Because it makes it harder to reject HO. Okay? If you look, like, okay, what did we have, what do we have for the p-value was 2.5%, right? And we had set the alpha value at 5%. That was in the Duke study, right? So because this was lower than this, it was deemed unusual. So they had convincing evidence of the alternative. Okay? But for some strange reason, sort of that was the Tokyo study, not it was the Duke study that corrected it. But for some strange reason, they just got a really weird sample or really weird experiment, the way the groups were split. Okay? If I lower this, if I say, because remember, we can raise or lower this. So if I lower this to 1%, now it's a different conclusion. Okay? I would say, okay, remember, we never accept HO, but I would fail to reject it. Okay? So that's why lowering the alpha level, except when you do that, it increases the other error rate. Does that help? And the problem that happens, usually because of that, is multiple tests. Okay? Often, to save money and to save time, organizations or people or universities or colleges or whatever, they don't just do one study, or they don't just test one thing in a study. They test a whole bunch of things. Okay? And what happened in the Tokyo study is eye contact time was only one of a whole bunch of things they tested. Okay? They tested a bunch of other things with those 17 people. So because of that, if you think you're going to make an error 5% of the time, and if you do a whole bunch of multiple tests, say 20, okay? Well, if you do 20 tests in a single sort of experiment, chances are one of those is going to be wrong, 5%. I mean, you did everything right. It just, because of probability, because of a weird sample, it just turned out not to be correct. Okay, so that's what happens when you do multiple tests. So, just to sort of wrap this, each test has a 5% chance of an error.
if we do multiple tests, and let's say I'm going to use 20 as an example because 20 is easy to take 5% out. Well, 5% of 20 is 1. So 5% of 20 equals 1 test will likely produce an error.
Just by, according to the laws of probability. That was a really weird last sentence. I just sort of, it's like I was falling.
Okay, the last thing,
And this relates to type 2 errors.
okay, we're not gonna, you do not need to worry about how to calculate what's called the power of a test.
Okay, we're only, that's beyond the scope of this course. I mean, I don't even know how to calculate the power of it. Okay,
But we can interpret it. So the power of a test is the probability of correctly rejecting a false HO. You reject it when you should have.
the opposite of that, a power,
Is the type 2 error rate.
okay?
When we, and remember what a type 2 error rate is, if you go back to the previous page,
Okay, when we should have accepted the alternative, but we didn't. Like we didn't reject a null, but we should have. We should have accepted the alternative.
so the type 2 error rate is always, because both of those add up to 1. 1 minus the power.
And this will be given to you as a decimal. And if it's a percent, you change it to decimal. Right? Because power and type 2 error rate add up to 100%. Or as decimals, they add up to 1.
So this could be an example you might see.
That relates to power. And this is just about interpretation.
So the Centers for Disease Control and Prevention claim that 11% of American children ages 4 to 17 have ADHD. Company claims it's developed a new vitamin tablet that will lower a child's risk for this. Researchers will administer the vitamin tablet to 200 volunteer children under the age of 4, with, of course, parental consent. They'll be tracked from childhood. Researchers will report the proportion of the subjects who develop ADHD. And they're going to perform this test because it's a hypothesis test at the 5% significance or alpha level, where the status quo is this claim: 11% have ADHD, children this age.
But the alternative hypothesis is that it would improve that, wouldn't it? So improve that doesn't mean greater. It means fewer would have it.
So that's why we say less.
Than 11%. Okay, that's what we're trying to prove.
So the new vitamin tablet is expensive to produce, so researchers would like to be convinced that it really does reduce it. Okay? And so they calculate the power of test to detect that P is 0.05 or less, is 0.937 or 93.7%. Okay, that's the power.
Common sense kind of dictates that obviously the higher the power, the better.
So this is quite a good power level.
So we would say, I got it right here.
If the true proportion of children who have ADHD, children who have ADHD is 11%. Status quo. There is a 93.7% chance we will find convincing evidence of the alternative hypothesis. Oh, no. That the true proportion will be less than 11%.
And then, of course, you could calculate the type 2 error rate by just doing 100 minus 93.7, and you get 6.3% for the type 2 error rate, which is pretty low.
And finally, just on the last page, I want you to just pick up this last one, please. I don't want to discuss that one. It's not really, we don't need to worry about it. So what can they do to decrease the probability of making a type 2 error rate and increase the power of the test? Well, make sure the sample size is larger. We've seen that yields positive results a lot of the time. Or increase the significance level, right?
Remember, decreasing the significance level
Decreases the chances of making a type 1 error. Increasing it decreases the chances of making a type 2. Okay. But